In this video, we're going to look at a basic example of a differential equation, in this case y prime equals y. Now this form, y prime equals y, can be written as dy, dx, t, s, any independent variable that we like. So I'll make it dy dx is equal to y, and then that shows the difference between these two forms for this differential equation. This one hides what the independent variable is in this case. Now, the idea of a differential equation is that it is an equation that involves derivatives of some function. So for example, here we have an equation that involves a function y of x and its derivative y prime. And so our goal is to be able to find a function y that solves the equation y prime is equal to y. So can you think of a function y of x that solves this differential equation y prime equals y? So just think about it. Can you think of a function whose derivative is equal to itself? So if you spend a little time recalling your differential calculus, you'll recall that d dx of e to the x is equal to e to the x. So we might say that if y is equal to e to the x, then y prime is also equal to y, which is e to the x. And so we see that e to the x is a solution to this equation y prime is equal to y. Any other guesses? Well, maybe if we guess y equals 2 e to the x. So in this case, note that y prime is also equal to the derivative of 2e to the x, and then this 2 passes through the parentheses by linearity, and it becomes 2e to the x prime, which is 2e to the x. This is again y. And so we see that the differential equation is also satisfied. Y prime equals y, y prime equals y, y prime is equal to y. So we're able to verify that 2e to the x is a solution to this equation, and also e to the x is a solution to this equation. Extending this idea of 2e to the x, we might make a guess that actually all solutions of the form c e to the x for any constant c solve this differential equation y prime equals y. Can we show that? Well, indeed, we can verify that y prime equals the derivative of c e to the x, which is equal to c e to the x, which is equal to y. And so we see that y prime is equal to y for any function of the form y equals c e to the x. So we have here an infinite number of different solutions depending on the constant c. This infinite family of different solutions is called the general solution. The general solution is a family of different solutions, each one defined for a different constant c. Y equals c e to the x is the general solution to the differential equation dy dx is equal to y. This is a differential equation because it involves the function and one of its derivative in an equation. We can specify one of the functions from the general solution by determining a value of the constant c from a condition. So for example, we might say a particular solution can be given by specifying a condition, sometimes initial or boundary condition, but really it's just a piece of information. We have one unknown, we need to have one condition in order to specify that unknown. So the idea is sort of like one unknown needs one condition. Two unknowns would need two conditions. Three unknowns, three conditions, and so on. So, for example, in order to find a particular solution out of this family from the general solution, we might say, suppose we're trying to find a function that satisfies this differential equation, y prime equals y. Okay, here are an infinite number of functions that satisfy y prime equal y. How can we also pick one that must satisfy a given condition, like y of 0 equals 1? So we have our general solution, y equals c e to the x, where this constant is not known. Now we plug in this initial condition to find that y of 0 equals 1. Notice this is saying x equals 0 and y equals 1. It's important when you look at a condition like this that you distinguish the independent and dependent variable. So y equals 1 when x equals 0. So in this case, when x is equal to 0, plugging that into y, we would have c e to the 0. E to the 0 is 1, and so this just becomes c, hence c equals 1. Therefore, we get a particular solution y equals e to the x, which is where c is equal to 1 in the general solution. So our particular solution to the differential equation subject to the initial condition, right? So it's a differential equation together with an initial condition gives us a particular solution, in this case y equals e to the x. You'll recall that y equals e to the x is the standard Euler exponential function that looks like this, which will be a thematic element of many courses in calculus studying differential equations. The exponential, oh, that's convenient, e to the x, but this is actually e to the x function. This is y, this is x, this is 1, and the domain is all real numbers. The range is 0 to infinity, exclusive of 0. It is actually of significance that the derivative is equal to the function defines this property. So for example, we say that the slope of the function is equal to the value at the point. So y prime equals y means when x is 1, then the value of the function is e to the 1, and also the slope of the tangent line to the curve is e, right? So this tangent line has slope m tangent equals to e, right? So the slope of the curve at the point is equal to the value of the function, right? E to the 1, which is just the number e. So this differential equation defines the slope properties of the function, and it also is a definition of Leonhard Euler's natural exponential function, Euler's function, or Euler's natural exponential function.